In this problem, we have a 75 kilogram diver who jumps from a board 10 meters above the water surface with an initial speed of 5 meters per second. We want to find the diver's speed just before striking the water. As always, our first step is to draw a picture. And in this situation, when we're dealing with a conservation of energy problem, or really any conservation problem for that matter, we're going to actually draw two different pictures. We're going to draw an initial and a final picture. Now initially, the person is jumping 10 meters above the water surface. And then in the final picture, we're going to have that person just before they strike the water surface. We're going to call the zero level the bottommost part. Usually we call the zero level the bottom part here. Then we're going to write down our givens, and we're going to write down our givens what we know in the beginning and what we know at the end. Well, in the beginning, we know the mass of the diver is 75 kilograms. We also know the height of the diver in the beginning is 10 meters. And we know the speed of the diver in the beginning is 5 meters per second. At the end, we know the mass of the diver is not changed. It is still 75 kilograms. However, the height of the diver is now at the zero level, so the height is 0 meters. The speed of the diver at the end is what we're trying to find. Now I'm going to label, the mass doesn't change, so I don't have to put any extra label on there. But since the height changes, I will label that as I for initial and F for final. And I'll label the speeds as I for initial and F for final as well. Now we're dealing with something called the conservation of energy. And the conservation of energy here, at least the conservation of mechanical energy we're dealing with, says that the total energy in the beginning, that is potential plus the kinetic, is equal to the total energy at the end. Again, that is potential plus the kinetic. What is going on in this situation is we're going to lose some potential and therefore gain some kinetic in its place. In other words, the diver is going to speed up. Now the potential energy formula for this one, we're talking about gravitational potential energy. So that'll be mgh. We're talking about the initial conditions. The kinetic energy formula is 1/2 mv squared. And again, we're talking about the initial conditions. That is equal to, again, mgh, but for the final condition, plus 1/2 mv squared, but again for the final condition. We can then place our numbers into our formula. We have the mass to be 75. G is always 9.81, and the initial height is 10. Then we have 1/2 the mass, which is 75, times the initial speed, which is 5, and that is squared. In our final conditions, again, we have the mass is 75, G is 9.81, and the height is 0. We have 1/2 times the mass, which is 75, and then our unknown, which VF, which is squared. We'll multiply all this out and add it. What we get here is that this comes out to be 7,357.5 plus this here comes out to be 937.5 equals, this all comes out to be 0, and then 1/2 of 75, which is 37.5 times VF squared. So it makes the equation a lot easier if we think of it in 4 parts. We have the initial potential, the initial kinetic, and find those numbers. Then we have the final potential, and then we have the 1/2 of the 75. Now I'm going to rewrite this on a separate sheet here just because I'm running out of room. So I have 7,357 and a half plus 937 and a half is equal to 0 plus 37 and a half times VF squared. Now we can combine these two numbers, and when we do, we get 8,295. On the other side, the 0 just goes away, and we're left with 37 and a half times VF squared. Now the 37 and a half is connected to VF through multiplication, so we get rid of it through dividing. Here it cancels out, and we are left with VF squared on the right-hand side. Left we get 221.2. And the final step, to get just VF, we need to square root both sides. When we take the square root of 221.2, we get 14.9. As always, we need our units. A speed is measured in meters per second.